Yo, what's up? All right, so my voice might not be quite as clear. I'm not using my mic. I left it at school, and of course, I am on location at the beautiful Shivi residence. Um, anyways, we're gonna get started here. 7.3, and let's get it right into it right away. So 7.3 is all about what we call the sample mean. All right. So 7.2 was all about the sample proportion, which would be percentages, and 7.3 is all about mean. So from here on out, basically there's going to be two sections in every book or every chapter. There's going to be one with the proportion and one with the mean. That's because we treat each differently with some different rules and different formulas. So you need to know the difference. So when do we use P most or percentages most, right? Because P would be our proportion, all right? When do I use proportions? Okay, well, when we have categorical data, all right? Okay, so for instance, if you don't know what categorical data would be, i.e., I don't even know what that stands for. I.e. Okay. Anyways, here's some examples. Brands, right? Okay. So, what's most likely? What brand is the top brand, or how many people drive Mazdas? How many people have an iPhone? All these kind of things, or what percent of people have an iPhone? All these things you can't put on a number line. So you have to say, all right, well, 23 out of 42 have an iPhone. And so we would put that and we make that into proportion. All right. When do we use means most often, right? Well, when we actually have numerical. Numerical. All right, data. Okay, and so this would be anything with numbers where we actually get weights, heights, IQ level, all that kind of stuff. We actually have numbers and we can put it on a number line. And when we have things that are on a number line, we can find the average. So, i.e., this would be a really good idea to look up what IE actually stands for. Who knows? Maybe it's a different acronym and I'm just saying IE. Let's say weight. I before E except for C or sound like sounding as A and when A we're in way. I think it's the other way around, guys. I think it's the I before the E. Well, maybe not. Weight, height, IQ, okay. Any of that kind of stuff when we have numerical data. Okay, so here's what we're going to get started off onto. So I have two distributions. First of all, here is the actual distribution of the population of household earnings in a certain town. Okay, so this is what everybody, where everybody's at. So I got some people that are making like 250,000. I got some people that are making zero. Okay. Um, and notice where's the mean of my household earnings. That looks like maybe around 70. I'd say about 70K. I don't know, something like that. Right? Okay. So this is the actual amount. That's everybody. Now over here, this is a sampling with ing. Notice distribution of, and let's notice down here, size 100. So basically, what this means is if I was to take 100 random people from this population, I have no idea how many people are in this population over here, but if I was to take 100 people and interview them about their household income, these are the different ways I could get 100 different values, right? I could not get a value way up here. It would be almost impossible to get values up here because, first of all, I had to have 100 people. And as soon as I start mixing in, there's one person, there's another person, there's another person, there's another person. As soon as I find averages, this high number is going to be averaged out and be lower anyways, right? So anyways, the average of all my 100 people that I interview is going to be right around here, right? That's sampling curve. All right, what do we notice that is the same? All right, so what are some things that we notice is the same? Well, I kind of already pointed out one thing. It looks like the center is at 70K, right? Okay, so center, I would say, is the same. Oh boy, center. Have I told you guys I write with a mouse? Holy mackerel. This guy right here, this is the culprit. Okay, shape. Is the shape the same? Ooh, no, because notice this thing's skewed right here. That baby's skewed. So I would say shape is not the same. Right? The center is shape, center, spread. What do you notice about the spread? Ooh, well, the spread here is only between here and here, right? The spread here is really far. So I would have to say shape and spread are different, right? And here's the deal: is like I couldn't do a z-score if I was just given one data. Like, what's the probability somebody has 100 grand? Normally you'd say, okay, well, 100 minus what I should have got is 70 divided by standard deviation. I don't know what the standard deviation is. Let's just call it 20. I have no idea. I couldn't do this. Well, I can find a z-score, but I won't be able to use my chart because this thing is not normal, right? Not normal. But check out, right? And that's if we select one person, right? One person. That's not really called a sample. I select one person. But if I start selecting multiple people, right? What are the different outcomes? What is the look of those different outcomes? What does it actually form into? Whoa, that's a normal curve, baby. And I should be able to, right? Can't do z-score on this guy, not normal, right? Can do z-score on this guy. Oh, you guys see this? This is some interesting stuff we're learning here, okay? So here's the important stuff. Write it down. The mean will be the same. So the mean of our sampling distribution should be the same as the actual mean of the population, okay? So remember, this means the mean of the sampling distribution, and this would be the actual population mean, okay? Here's something really cool. The standard deviation of a sampling distribution is this right here. New formula, jot it down. New formula. And basically what happens, the same thing with proportions, the more I sample, the less skewed I can get. I'm going to keep approaching that actual value, and I'm going to be able to get less and less options out to the edge. So as I sample 1,000 people from that population, it would be even skinnier. Okay. And then, of course, the standard deviation works only if the 10% condition is applied. And we have talked about that before, so I'm not going to go into depth. If you're really interested, I think that's like 7.2 lesson 1 if you want to listen about that. But you can't have more than 10% of the population. Otherwise, it won't be independent. Okay? Well, it's still not independent even if you do take out, but we're allowed 10%. Okay? New formula. So as I start sampling more, my sampling distribution is going to go down. In one simple case, there's a simple relationship between the two distributions. The population distribution is normal. Oh, snap. And so is the sampling. This is true no matter what. You know what? I think I'm missing a chunk somewhere. Where does it say? I think it might be the next slide. This doesn't really work. Here, let's go to the next slide. All right. For Mr. Sheevy's video on sampling distribution, he has made the correct sampling distribution for samples of 30. I had to actually make, I don't know if you guys remember watching this video or not, but I had to make a sampling curve for a sample of 30 because if you listen, I had to make it, right? I formed it right over the top of this. So how would I form it? What does it need to have? So it says draw the correct sampling distribution curve over the population. Well, we know the population mean is 5.8. So we know if this is the population mean, that's also going to be where my sampling curve peak is going to be too, as well, right? Because we know those are the same. And let's just do this right here. Let's make this a little bit more All right. Now here's the trick. What I had to do is I had to take this standard deviation and I had to divide it by the square root of n. Now I'm taking 30 samples, so the standard deviation is going to get smaller, right? And if I was to just take one sample, the population deviation is really what I'm going to use. But since I'm taking 30, and remember what happens as I select more, right? This would be basically like sample size of 1. I don't know if this makes sense to you guys. This is sample size of 100. What happens? Ooh, it gets skinnier, right? So that is why we have to use this formula here, right? We take our actual standard deviation and we divide it by square root of n. So here we go. Let's calculate that out, shall we? All right, so I got a value of 0.822. So that means my sampling distribution is going to be quite a bit smaller. What I did with that was I actually multiplied it times 4 because I know sampling curves only go out about 4 deviations. And so I should really go out to only about 3 deviations, 3.28 above this. So let's say 1, 2, 3. That's about where it should end. And let's go 1, 2, 3, like right about there. So my curve should really be something like, peaked it up, come on back down. It should be normal, 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 something like that. Okay? Those are the different ways I can outcome. So can I get a result of a 10? The odds of that is almost impossible, right? The odds of getting sampling 30 people and getting the mean of 10 for my sample is almost impossible. Like pretty much near impossible. All right, moving on. Really, the meat of the story here is central limit theorem. I don't know why they named this one. They didn't name the percent one, but the central limit theorem basically says, how do we know when it's going to be normal? How do we know when a mean type problem is going to be normal? For instance, if this is the population, this definitely is not normal, right? That is way not normal. Okay. How do we know? How many samples do we need to do before it turns out to be normal? So here's a sample of 2. Is that going to be normal now? No, it's looking a little bit more put together, but not. Here's a sample of 5. Ooh, it's starting to really look normal. Even with 5, it's starting to look pretty normal as far as outcomes is concerned. If I sample 10, sample 25, notice by 25, this baby looks, these are the different ways I can get 25 samples, different ways, and it means from the same population, right? Because if I take like 2, all these dots here and a couple dots here and a couple dots here, they'll average together and be like right here, right? And so what's the central limit theorem? I don't know how you're going to remember this. CLT. I don't know. You got to remember it though because it's on tests and quizzes. Central limit theorem basically says if you have a sample size that is greater than or equal to 30, okay? Doesn't matter. Does not matter the shape of the original, okay? Yeah, it's skewed as all get out. You have a sample of about 30 or more, this baby's normal, okay? Our sampling curve will be normal, okay? So here it is officially. Population distribution is normal, then so is the sampling distribution. Oh, by the way, yeah. So if the population says, oh, by the way, it's normal, then do you need to sample 30? No. Okay. If the original thing is normal, then the sampling curve will be normal. Doesn't matter, right? Doesn't matter no matter what the sample size. If the population distribution is not normal, so if this thing is like wow, look at that. That's really skewed, right? The central limit theorem tells us that the sampling distribution of X will be approximately normal in most cases if we sample more than 30. All right, so it doesn't matter what this looks like. As long as we sample 30, we will have a normal distribution for our sampling distribution. All right, so last thing on our must-haves. So pretty much what Chapter 7 is all about. And next lesson will be all math, guys. Here it is. Normal test. N is at least 30. Okay? Why do we do it? So we can use z-scores and our yellow sheet. It's the same reason why we do it over here. Just realize these two are not the same. Everything else on this sheet is the same, just not the two normal tests. Okay, over and out, guys. We'll see you on Tuesday.